ideia agora deixar maior. Data de clicador. Deixa assim. Tá.
Acho que esse é uma fica.
Deixa assim. Já botou YouTube? Pedro, pode ver se está transmitindo. So welcome everyone to today's seminar. Today we have Søren Larsen from the Radboud University in Nijmegen in the Netherlands. Søren received his PhD from the University of Copenhagen in 1999 after postdoc positions at the Lick Observatory in the US and ESO in Garching. In Germany, he moved to the Netherlands in 2006, first to Utrecht University and in 2012 to Nijmegen. He is a member of the Euclid and MOSAIC consortia, and in MOSAIC, he co-leads the science working groups on resolved stellar populations. He has also recently translated the Johannes Kepler's book, the first theoretical description of the telescope. Søren, it's very nice to have you visit. You may start when you're ready.
All right. Thank you, Anna, for the introduction and for organizing this visit here. It's great to be here in Porto Alegre in Brazil. It's actually my first visit. So the reason that this visit really came about was, as Anna mentioned, the involvement that I have in MOSAIC, the spectrograph that we're building for the ELT, together with Brazilian colleagues. So next week there is a meeting about that and other things in Sao Paulo, where I'm going to talk a bit more about MOSAIC. But I think one of the exciting things about MOSAIC is that we're really going to be able to take stellar population studies to other galaxies beyond the Milky Way in a level of detail that we've not been able to do before, right? Really getting spectra of individual stars and, of course, globular clusters of galaxies well beyond the local group. And so then we can start to answer this question even better that I phrase here at the top. How typical is the Milky Way? That's, of course, a very generic question to ask. But my sort of entry point into this is observational studies of the old populations that can tell us something about galaxy assembly. So how did galaxies come together, build up over time? And of course, in the Milky Way, we know a lot, right? The background image here, these fireworks here, that's the streams identified in the Milky Way halo by Gaia and other surveys. And so we now have an incredibly detailed picture of how the Milky Way initially came together from all these dwarf galaxies and satellites that came in and were accreted. And with Gaia, we can identify those things in a variety of ways, in phase space, but also through chemical abundances, which I'm going to talk a little bit more about later. So in the Milky Way, we have very much detailed information, but the Milky Way, of course, is only one galaxy. So even though that fits the hierarchical assembly paradigm, what we see in the Milky Way, to really get a statistically significant comparison with models, we need to look to other galaxies. And it will always be the case, of course, that the Milky Way is the galaxy that we live in. We can observe that in the greatest detail. We have almost 2 billion measurements from Gaia of stars in the Milky Way that will not in any near future be the case in external galaxies. But of course, what we gain there is larger samples of galaxies than just one. So that's, I think, part of the motivation for taking this kind of work to other galaxies. And you can also see here that actually we have the stream factor. We also have globular clusters that are labeled here. So many of those, oops, something happened here.
It will just rejoin and then
We'll come back.
I think you have to share the screen again.
Let's try it again. There it is again. Okay, yeah. So you can see here, of course, these globular clusters here. Some of them are just individual globular clusters where you see the streams from the clusters as they're losing stars. So that's part of the streams that we see. But we also know that some of the fragments that came in and built up the galactic halo, they actually contributed more than just one globular cluster. And we can identify those globular clusters and actually associate them with specific progenitors, and that helps us pin down things like age and metallicity relations. And so that kind of work we might also be able to do in external galaxies where we maybe cannot identify the individual stars so easily, but globular clusters is something that we can look at. So I will get back to the globular clusters in a little bit more detail later. Let's see. How do I switch here? I got some strange ones here.
I think if you click on it, then it should.
Okay, now switched. It may be a while before it appears. Okay, there we are. Yeah. So this is just a little reminder of some of the tools that we have to work with when we do these kind of studies. This is from the Gaia and Enceladus paper. Right? Gaia and Enceladus is this last major accretion event in the Milky Way. And of course, we have color magnitude diagrams that come typically from imaging. Right? So we need imaging, and then we can use those to learn something about star formation histories. And then we have chemical abundance space here. So this is you cannot see this really, but this is alpha over iron abundance ratio versus metallicity here. And so you see here that the different components of the Milky Way, thick disk here, the thin disk, and then the Gaia and Enceladus stars over here that occupy different regions of this parameter space. So that's also kind of things that we hope to be able to do in external galaxies. Maybe not always with individual stars, but with globular clusters. So that's spectroscopy, of course. And then we have on the bottom panel here, kinematics. So again, you see the Gaia and Enceladus stars standing out in a distinct part of kinematic space. So those are the kind of traces that we also can use. And this is then a combination, of course, of imaging and spectroscopy nowadays, at least in the Milky Way, right? So we get all the dimensions of phase space. In external galaxies, that may vary a little bit depending on what we're looking at, what we can actually do there. This is a rapidly evolving field. There's a lot of new instrumental facilities that are coming online in these years. On the bottom here, I have some of our old tried and trusted facilities that we use, right? Keck telescope and VLT. There are many others that I could have put on here, right? But those are the ones that have played sort of a prominent role in some of the work that I've been doing, and that I will talk about a little bit later. This is the William Herschel telescope on La Palma. With the Weave spectrograph here, which is one of these new generations of instruments that will do surveys of large numbers of stars in the Milky Way, following up on Gaia. Gaia's spectroscopic capability is limited mostly to the brighter stars, and we have surveys like Weave and Foremost and many others that are then following up spectroscopically the fainter stars. So Weave is been a little bit delayed, but hopefully the observations of the surveys will start soon. We've already got some IFU data that I'm actually not going to talk about today, but the instrument has been operating for a while, at least in some parts of its space of the capabilities that it has. And then we have, of course, Euclid here. I'm going to get back to that in the last part of the talk today. The first major data release, DR1, is about to go public in a couple of months from now. So that's going to be, I think, exciting for a lot of people. Internally in the consortium, it's already been available for almost a year now. But I'm not going to talk about that too much today. I'll show a few results from the early release observations that are all fully public and have been published, just to give a little bit of a taste for what Euclid can actually do. And then, of course, here in the middle, this is the ELT, right, that will come online in a few years. Under construction on Cerro Amazonas in Chile, first light in a little over 3 years from now, first technical light, end of 2029, and then first scientific observations the year after, 2030. So that's sort of a little bit, but depending on how long your PhD takes, right, but sort of the time scale of a PhD, right? So it's getting real, and you can follow, progress on the webcam if you search for the ELT and see how things are going. So from the outside, the dome looks more or less ready, but of course there is still a lot of work to be done inside, installing mirror segments and electronics and wiring and all these kind of things. Thanks. So this is just a little overview. I'm not going to spend too much time on the specific instruments because there's also going to be some lectures about this later on this week. I'll talk about ELT instruments and the science cases in a bit more detail, but this is just to outline what the focal plane looks like, basically. Right? So you can imagine looking at a nearby galaxy here, like NGC 300, and then you have the different instruments. And MOSAIC here is the only instrument that makes use of the full ELT focal plane field of view, which is about 7 arc minutes across. So that's 40 square arc minutes, where you can then put fibers on different sources there and get infrared and optical and low resolution, high resolution spectra. And then we have the Mikado camera here, right? That also has a high resolution and low resolution mode that will go very deep and provide very high astrometric quality imaging as well. We have Andes there, the high resolution spectrograph, and we also have METIS, the infrared instrument, and then Harmony, the physical field unit there. Okay, so before I then progress to the next steps, I will just, if you allow me, go back in time a little bit and talk about this book here that Anna also mentioned, the book The Optical by Kepler. So he wrote this book after he had heard about Galileo's observations that he had made of Jupiter's moons and other things. So I thought it would be nice to actually make that book available for an English reading audience rather than Latin. Kepler, of course, wrote everything in Latin, but I translated this into English. And it's quite a nice book to read, actually. So it's the first theoretical description of how a telescope works. Galileo didn't provide that description, Kepler did that, but there's also in the introduction to the book an exchange of letters between Kepler and Galileo, where Kepler provides his thoughts on all the discoveries that Galileo had made. We should also recognize that Galileo was maybe the best at publicizing these discoveries that were made with the telescope early on, but he was not the only one to use the telescope. He also was not the person who invented the telescope. He did not actually claim to invent the telescope. So he said that he heard the rumor about this perspiculum that had been constructed by a certain Dutchman back in 1608, and then Galileo decided to improve it and, of course, to look up. But there was also this German astronomer here, Simon Marius, who made basically the same discoveries around the same time. Those discoveries were, of course, craters on the moon. You can see stars that are much fainter than what you can see with the naked eye. And then the serendipitous discoveries, right? Jupiter's moon. So about half of Galileo's book here, the Sidereus Nuntius, that's about Jupiter's moons, how we observed them night after night and saw initially 3 and then 4 moving around Jupiter. And that was maybe the most impactful discovery that was made, both by Galileo and Dr. Marius, and also for Kepler, very fascinating. Then there were other things. So this is an excerpt from the book where Galileo writes about his discovery of the phases of Venus, right, where at first it was perfectly circular, then it started to be sort of a little bit less circular, and then it thinned into a crescent. And this then proved 2 things, right? This change of the phases of Venus, namely, first of all, that the planets do not shine with their own light. They shine with reflected sunlight. That was still a question at that time, but the fact that Venus shone phases, that proved beyond doubt that this was the case. And then, of course, the fact that Venus is going around the sun. So if you were a 17th century astronomer, you could say this is probably the kind of thing that you would have put into your science case for the telescope, right? Say, if you're going to build a new instrument that can illustrate, that can teach us whether the Ptolemaic system or the Copernican system is right, okay, we should look at Venus and try to see if there are phases or not. Yeah. But Jupiter's moons is not something that someone would have thought of looking at, right? It was just, okay, what is that bright thing there in the sky? Let's see how it looks, right? And sometimes those are the more impactful things. So that is sort of the reason for this short digression here, right? Sometimes it's useful to step back and learn a little bit from history. And of course, whenever we get new capabilities, like the telescope or the ELT or anything like that, we get new discoveries, but actually our ability to anticipate and predict what the most impactful discoveries will be is quite limited. Nobody would have predicted there should be 4 moons orbiting around Jupiter. Right? So we should keep an open mind as we keep exploring the world and the universe. Okay, so that was a little bit of a historical digression, and then back to now and to the future, and I will then move slowly in the direction of globular clusters, specifically as halo tracers. So I think in this audience here, I maybe don't need to spend too much time justifying why globular clusters are interesting. But I just want to spend a few minutes anyway to remind you that actually some of the first evidence of the hierarchical galaxy assembly paradigm came from studies of globular clusters, right from the Søren paper here, where they looked at the metallicity versus galactocentric distance of globular clusters and saw that you did not observe this very strong correlation that one would have expected in the simple monolithic collapse picture, right? You needed something more complex. So that was sort of the start of the whole hierarchical galaxy assembly paradigm. And nowadays, we can actually identify a significant fraction of the Milky Way globular cluster system with fragments that have come in and have been accreted. The same is true undoubtedly in other galaxies. Right? So this is a map of stars around M31 from the PANDAS survey. So the background grayscale here, that's just the density of RGB stars. And then you see the colored dots here, those are globular clusters that are actually spatially correlated, quite high level of significance with where the stars are. So it's clear that also in M31, the globular clusters trace the assembly history in quite significant detail. And in the outer part of the halo, it's a very large fraction that are thought to have been accreted. Okay, and in the Milky Way, as I said, we can identify globular clusters now in considerable detail with specific accretion events. And this is work by Davide Massari, where he showed that when you then plot the age metallicity relations for globular clusters associated with different progenitors, they are actually different. So you see the colored dots here are globular clusters associated with different accretion events. And so we also learned something about those progenitors beyond simply being able to identify them, right? We can actually learn something about their star formation histories and their chemical enrichment histories. And the globular clusters are quite nice in that respect, right? Because this is this kind of things that we will also be able to do in external galaxies. And there's no doubt that, as I said, other galaxies also have undergone accretions. So this is work from about a decade ago or so, showing M87 here, where based on kinematic evidence, there seems to be clusters that are grouped together here and probably came in from some kind of dwarf galaxy that was accreted. But we know nothing about the chemistry of these clusters, right? This is something that has to await the ELT or other big telescopes of that class. So this slide here, in a sense, is representing the same thing that I showed for Gaia and Enceladus earlier on, right? So we have the kinematic evidence here. We would also like to have the chemical evidence. We are not there quite yet, but we know that there are certain abundance ratios that, at least in the Milky Way, seem to trace the origin of stars and globular clusters quite nicely. So this is, for example, europium versus silicon, where there seems to be a division here based on the assembly history of the sources, right? So things here on the bottom with lower ratios seem to have formed in situ, and the ones here on the top seem to have been accreted. And so I will show a little bit later that this can probably also be applied to external galaxies. This panel here will be shown a little bit larger, so you can see what's actually going on. But there are some clusters there that are a little bit outlying, some of which may have been accreted. So these are local group globular cluster abundance measurements. So that actually transitions then into some of the work that we've been doing on local group globular clusters. And this is very much with the idea in mind that in some years from now, we'll be able to do all of this on a much grander scale with things like the ELT. So our goal in this project here was to measure detailed chemical abundances for local group globular clusters, and of course, develop all the techniques that will eventually be needed for analysis of ELT instrumentation. So this is something that we've been doing, but also other groups by Sakai and Colucci and others. We have about 46 globular clusters or so that have been observed with high-res and UVis, so high-res on Keck, UVis on the VLT, at a signal to noise that's sufficiently high that you can measure individual chemical elements. So here's a list of the ones that we've been measuring. The ones that are red there are ones where we have applied corrections also for non-LTE effects, which is nowadays sort of a standard thing to do for individual stars. But for globular clusters, we can now also do this. And in some cases, I have one slide a little bit later that shows that this can actually make a significant difference, whether you apply those corrections or not. So that's something you have to worry about, but something that we can do. Okay, so those are the galaxies in the local group there. Just very quickly, again, I'll talk more about this tomorrow. And you see here how we do this kind of analysis. We basically do full spectral fitting here to, this is a globular cluster spectrum, 47 Tucanae here. And you see some lines labeled here, sodium lines here, and also over here, right? So sodium is one of the elements you might want to look at. And on the bottom here is the spectrum of Arcturus, individual red giant, right? And of course, there the lines are all very well, nicely, clearly separated. So you could even just measure them one by one, the equivalent width. But once you go to globular clusters, they become blended with other lines. Even though we observe at high spectral resolution, the clusters themselves have velocity dispersions of several kilometers per second. So in the case of 47 Tucanae, this is what you get, even if you would observe that basically with an instrument that has infinite resolution. So, but you can compute model spectra, right? And if you have a line list that is good enough and includes all the lines, then you can fit for different abundances there and get results up there. So once you have a model that fits here, then you hope that that actually gives you the abundances. Again, I'll talk more about this tomorrow. Just go on to the results here. Right? So going back to some specific ratios, right? These are the alpha elements that I talked about a little bit earlier, right? So they basically trace the contribution from type 2 supernovae versus type 1a supernovae to chemical enrichment, right? So alpha elements are things like magnesium, silicon, and calcium, titanium, and also oxygen, right, that are produced in type 2 supernovae. And then we show them relative to iron here that comes mostly from type 1a supernovae. And of course, the time scales on which these different supernovae contribute to chemical enrichment are different. So by looking at these abundance ratios here, we can learn something about the time scales for star formation when these globular clusters were formed. So to first order, you see, so the colored symbols here are globular clusters in these local group galaxies, and the gray symbols here in the background are individual stars in the Milky Way. And we see that these alpha elements are all enhanced. That is true both in the Milky Way field stars and also in the globular clusters. So that is, to first order, at least consistent with the picture that we are seeing old stellar populations here that formed quite early on when type 2 supernova nucleosynthesis was still dominant. I have blanked out the top there, but I will show it now. So that's magnesium, because magnesium is not quite as nice. So for calcium and titanium, the scatter or the dispersion in the abundance ratios is actually quite small. And a significant fraction of these 0.1 decs here come just from the measurement of certainties. Silicon, the scatter increases a bit, but the silicon lines are weaker, and you can see that the error bars have become bigger, right? So it's just harder to get a high precision for silicon. But for magnesium, there seems to be something else going on, right? Most of the globular clusters, they lie up here where the field stars are, but there are many, or at least a significant fraction, that fall below here with very low magnesium over iron ratios. And that's something we haven't still quite understood, I think, what is actually going on there. So maybe that there's some interesting things going on there. Now you can look at this plot here and these diagrams in a little bit more detail. So these are those outliers that I alluded to in one of the previous graphs. So there's like 2 or 3 clusters there that have low abundance ratios, not just of magnesium, but also of silicon, calcium, and titanium. So what is going on there? Well, there I think we're just seeing basically the signatures of chemical evolution in the galaxies where these clusters belong. Right? So one of these is actually the most metal-rich globular cluster in the Fornax dwarf. One of them is the most metal-rich globular clusters in NGC 6822, and one of them is an M33 globular clusters. So for Fornax and for NGC 6822, you're probably just seeing the sort of typical relation that we see when we plot alpha to iron abundances versus metallicity, namely that this ratio is enhanced at low metallicities, and then you have this knee here where the type 1 supernovae start to kick in, right, and produce more iron. And that happens at different metallicities in different galaxies, depending on the evolutionary history of that galaxy. But if you just sort of draw a line here by eye, this dashed line here, the colored symbols here are now measurements in dwarf galaxies, right? You can see it also sort of goes through these outliers here. So I think that's basically showing us that the globular clusters trace the chemical evolution that we also see in the field stars. Then there are these guys over here, right? They are a bit harder to explain why those clusters are so extremely depleted in magnesium. So there are different things that could be going on there. When we talk about globular clusters, of course, some of you may have heard about this puzzling problem of multiple populations. We know that there are abundance anomalies in globular clusters. Certain light elements don't behave in the way that we see they behave in the field. So there's sodium and oxygen that are anticorrelated, and magnesium and aluminium as well, right? So magnesium is one of the elements that is involved in those multiple populations. But there are no Milky Way globular clusters that would fall all the way down here if you would just observe them in the integrated light. So I don't have slides showing that in this particular talk here, but one of the clusters that we have looked at with WEAVE is NGC 2419, which is an extreme outer halo globular cluster, which has a very extreme magnesium spread, but it would fall somewhere up here around 0 if you would plot it on this diagram. So there really should be, I think, something going on with some of these clusters here. But there are studies of dwarf galaxies, so some of the ultra-faint dwarfs also have rather strange chemical, or let's say unusual chemical abundance ratios. So this is Carina 2, where you can see here magnesium over calcium versus iron, and there are some stars there that actually have quite low magnesium over calcium ratios as well. So the suggestion that was made, a little bit hand-waving in this paper here, was that maybe there's something funny going on with the IMF, but I think we are still quite a long way from understanding really what's going on there. Okay. Now, I'm not going to go through the full list of all the elements that can be measured here. I'm just going to show a couple of examples here. Right, so we can do a principal component analysis. PC1 is just metallicity. PC2 is basically the alpha elements and other elements that correlate with those, right? So you just ask basically how many dimensions are there in this abundance space that we can measure. If one, of course, is total metallicity, and the next higher order effect is then the alpha elements and other things that vary together with them, like sodium and scandium, nickel, and zinc. And if you then project the measurements back on top of these principal components, and this is PC1, so basically metallicity, and then PC2, accounting for all these elements here, then you again see those three outliers there standing out now quite clearly. And so I have discussed which ones they are, right? Fornax 4, NGC 6822 cluster 7, and then this cluster M33 that we sort of suggested in this paper here, that maybe that indicates some sort of accretion origin for this cluster, right? That it came in from a dwarf galaxy. That was a little bit speculative, but I was actually quite excited then last year when a paper came out from here from Anguiano, where you see that they looked at kinematics of local group globular clusters, and they showed that exactly this cluster over here, HM33B, I think it was supposed to be marked. Maybe it is not. Okay, it's not marked. Okay, but is this cluster? There was supposed to be a circle here, actually, right? So maybe that is a circle that has shifted. Should be down here, right? So this cluster stands out in this space of action angles, right? So these are clusters that would follow normal prograde orbits, and basically this cluster here has a retrograde orbit, showing again that maybe it came out, and that is then sort of in line with what we expected chemically. This is from another paper that's in preparation, showing this europium versus silicon abundance ratio, And again, cluster B in 33 lies up here. These blue and red sequences are basically the accreted and in situ sequences. Right? So you're seeing that we're starting to maybe get some hope that we can learn interesting things about chemical enrichment and assembly histories of galaxies by applying this in the future to larger samples. This is still a relatively small number of clusters, but with MOSAIC, you will get as many clusters as we have in this whole program, right, in just one observation, right? So we can take this to a much larger scale. So these are the kind of things that we were hoping to do. Then a little bit about the details that they matter sometimes, right? Manganese here is an element that lies right next to iron in the periodic table. So you might expect that the nucleosynthesis would be quite similar, but actually the amount of manganese that's produced is sensitive to the exact mass of the type 1a supernova progenitors. And you can interestingly fit the observations here, so manganese versus iron, with whether you make non-LTE corrections or not. Right? This is just taking the standard LTE, local thermodynamic equilibrium analysis. You can fit them with a model here, where all the nucleosynthesis comes from type 1a supernovae. But if you then apply non-LTE corrections, you see that this relation here actually flattens a lot. And then the preferred model becomes one that has a combination of type 2 and type 1a supernovae that produce manganese. And also the masses of the type 1a supernova progenitors then become different, right? So in an LTE case, you actually prefer progenitor masses that are somewhat below the Chandrasekhar mass. So you can learn something not only about galactic chemical evolution, but maybe also about stellar evolution from these kind of studies. And sometimes then you need to worry about details like non-LTE effects. Okay, so that was sort of the expected. Right? These are the kind of things that we were hoping to do when we set out to this work, but sometimes you also come into this serendipity regime, right? Like the moons of Jupiter. And then in this case here, we found this very metal poor globular cluster X8 that I just wanted to briefly mention here as an example of those kind of unexpected discoveries. So there was not even a cluster that was part of our regular program, and we had an observing program to look at M33 clusters, but at the beginning of the night we had to wait for M33 to rise. So we thought, well, let's pick some random cluster in M31. This one is X8 that had not been studied in too much detail before. And it was clear just from looking at the spectra then, when you plot them up, that the lines were really very weak. And so the blue spectrum here, that's then X8, right? And is compared in orange here with the spectrum of M15, which is one of the most poor globular clusters in the Milky Way. And you don't need to do any analysis. Just by looking at the spectra, you can tell right away that this blue one X8 is significantly more metal poor than M15. And when you do the analysis, you get a methodicity of -2.9 in LTE or -2.8 if you apply non-LTE corrections.
It's quite far from the galaxy, right?
Yeah.
You
can see it's out here, right?
Yeah.
It's I forgot now. It's something like 25 kiloparsecs out in prediction. So it's like extremely far out, right?
Far out, yeah.
But, of course, along the line of sight, we don't really know. Right? Yeah. There we go. So why is this interesting? Well, there's this notion of the globular cluster metallicity floor. Right? So in the Milky Way, the metallicity distribution sort of cuts off at -2.5. And you can wonder, why should that be the case? Is it just statistics? Right? Of course, there are not so many metal poor stars either, right? But if you compare with field star metallicity distributions or simple chemical evolution models, you would actually expect something like a handful of clusters there down below -2.5. So that has given rise to this metallicity floor. Why might that be the case? Right? And part of it might be actually the way that galaxies come together. Right? We have again the hierarchical picture where we think that bigger galaxies are built up of smaller fragments, and these all have their own mass metallicity relations. And you would expect that a globular cluster should have a metallicity that is less than the metallicity that corresponds to a mass of a given fragment according to the mass metallicity relation. Okay? So that's maybe a little bit long-winded way of saying it. Here we have illustrated graphically how that works, right? This is metallicity. This is mass converted into luminosity, right? And these are sort of generic mass metallicity relations that are applied based on observational constraints also, right? Redshift 3, redshift 5. Right, so galaxies would typically fall along these lines here, depending on the redshift exactly. And so you would expect clusters that form within galaxies to lie below these lines, right? A cluster should be less massive than the galaxy in which it forms. And so that sort of makes sense. By the time you get down to a metallicity of -2.5, right, you don't have any globular clusters anymore, but also the galaxies don't seem to be massive enough to form globular clusters, right? So maybe that's why there is a cut there. Until you then plot X8, right? It lies there, way above the mass metallicity relations for galaxies, right? So that's what makes it interesting, right? And again, this is just one cluster, but it was a little bit unexpected to find something like this, right? And of course, we had to go back then, and people have to, not me, but someone else has to see if this can be accommodated in the models for galaxy chemical evolution, right? They'll probably have some scatter, right? And maybe it's very rare to find an object like this. Maybe there are more of them out there. We haven't found any more so far, right? But that's also something we might want to look for. There are in the Milky Way halo some somewhat similar cases, right? C19 is not an extant globular cluster, but it's a stream that has been identified with an even lower metallicity, -3.4. So that's definitely below the metallicity floor, but also with a lower estimated total mass, right? So there may be more of these things out there waiting to be discovered. Okay, so that was the spectroscopy part, right? And I'm not sure how much time is left. Maybe not so much.
No, you have 15 minutes.
Okay. Yeah, we started a little bit late, I guess. Yeah. So I wanted to say a little bit about Euclid here at the end, right? Just a little teaser of what's coming on. So I don't know how familiar people are with Euclid here. Right? This is, of course, an artist's impression. It was launched now, it's hard to believe, more than 3 years ago. It's a 1.2 meter telescope, and it has these 3 filters here, right? 3 infrared, near-infrared filters, Y, J, and H, and then this very broad this filter here, which is designed for optimal throughput, right? Euclid is aimed at cosmology, right? So what cosmologists want to do with this broad this filter here is just collect enough light to measure the shapes of galaxies for weak lensing studies. But of course, we also get nice imaging of whatever nearby galaxies happen to fall within the Euclid field of view. So this is a survey that's coming up here, right? So this is the whole sky. Again, because the mission is cosmology driven, it is observing high galactic latitudes, right? This is the plane of the Milky Way. And it's also avoiding the ecliptic plane here where the sky background is higher. But we're still getting something like 13,000 square degrees of extragalactic sky, including things like the Fornax cluster that lies down here. Unfortunately, the Virgo cluster is over here, right? So, but okay, we get the Fornax and we get things like the sculpture group eventually that will fall a major one group here and so on. So there's plenty to do also for local universe studies, and of course looking also at the halo of our own Milky Way, something that we can also do with Euclid as well. So it's impossible for me to talk about everything that we'll be doing with Euclid, so I'll just focus on a few things that are of relevance to this talk here, and then advertise, as you may be already aware, that DR1, the first about 2,000 square degrees, are actually going to become public in just a couple of months from now. And then you can go and have a look. But I'll show a few results from what's called the Euclid Early Release Observations Program. So these were observations that were made before the survey actually started. So there are different targets that were being looked at. This is from a program called A Nearby Galaxy Showcase, led by Leslie Hunt, basically showcasing Euclid's ability to image nearby galaxies. So there were 6 galaxies that were observed in this program. I will talk about mostly the 3 on the top here, IC342, NGC 2403, and Holberg 2. So those are all at distances about 3 megaparsecs, where the Euclid can actually still resolve the red giant branch. And these are local galaxies that have been studied in a paper by Jess Howell as well. Okay, so overview of the galaxies. This almost looks as if it were by design, but it was actually more or less, well, it was not quite a random selection of the galaxies, but it was a selection that was driven very much by observational constraints of what Euclid could observe in the period that was available. So IC342 is basically a Milky Way analog, or M31 analog in terms of luminosity at least. NGC 2403 is basically an M33 analog, and Holberg 2 you can think of as an SMC analog in terms of luminosity and morphological types. So we thought it would be interesting to contrast the globular cluster populations of these three galaxies with the globular cluster populations of the corresponding galaxies in the local group. So here's NGC 2403, the Euclid image. So you see galaxy quite comfortably covered at 0.7 by 0.8 degrees, and the red circles here are the globular clusters that were confirmed prior to Euclid in NGC 2403. And then in the Hunt paper, we found a few more. There we go. First, there's a blow up here where you see the level of detail into which these galaxies are resolved. So that's really quite nice to look at. And there we are. Okay, yeah. So in the Hunt paper, we looked mainly at outer parts of the galaxy, found 8 new globular clusters that were not included in any catalogs before. And then in a more detailed study, we also looked more towards the inner regions of the galaxy. So now we're at about 50 total, and that turns out to be more or less what you would expect for a galaxy of that luminosity. That's also the estimated number of globular clusters in M33. And just zooming in on a few of them, right? This is one of the known ones, D6. And this is another known one, F46. Gets a little bit trickier once you get inside the galaxy, right? Of course, there's also field stars that it's a bit hard to tell whether this is actually a resolved globular cluster or not, or some background galaxy. But this one is known spectroscopically to be a globular cluster. This one down here is one of the new ones, clearly resolved into individual stars. But also you can go back and look at things that are present in catalogs as globular cluster candidates, and then check whether they're actually globular clusters. This one is clearly not, right? This is just a star. You can see the diffraction spikes there, but it's actually a binary, or at least 2 stars close together, right? So that's probably why it looked a little bit fuzzy in ground-based imaging. And there's another thing here that was also as a globular cluster candidate, but this is a galaxy, right? No trace of resolution into individual stars. So that's also an important part, right? Not just discovering new things, but also sort of going through what is in literature, right, and verifying whether things are clusters or not. And so what we get with Euclid, of course, is the coverage of this very wide area. So the ERO observations were individual targeted observations. Imagine now that we get 13,000 square degrees where you can zoom in like this, basically anywhere you want within that whole coverage. Right, so this is illustrating the candidates were found in NGC 2403 and in IC 342. You cannot really see it so well here, but I've overlaid the HST coverage that exists of these galaxies if you want to see a better version of these figures, and find them in the paper that we published that shows this. But the point is that of these nearby big galaxies, typically only a very small fraction has been covered by HST. Certainly in the outer parts, so there's a lot of room for new discoveries and going and looking at these images. IC 342 is actually a little bit on the low side compared with the Milky Way and M31. So these are the number of candidates that we have found. I don't really have too much time here to go into all the completeness analysis and so on, but we can look at the number of clusters that are brighter than the turnover, which is about -8. So that's probably about half of the population. There's about 45 of them, right? So in the Milky Way, that would be more than that, and in M31, certainly a lot more. So IC 342 actually seems to be a little bit cluster poor compared with both the Milky Way and M31. And this circle here, I forgot, I think I told you that at 10 kiloparsecs or something like this, and there's actually very few clusters outside of that, right? And so you may find that a little bit surprising, but if you would do the same for the Milky Way, it would not actually look all that different, right? Half of the Milky Way globular clusters are, most of the Milky Way clusters are actually quite close to the center. There are a few, of course, large galactocentric radii, and those may be interesting, but it's not so surprising that we don't find a huge number out of large radii. Here's Holmberg 2. It's a galaxy that has been studied by HST, but still we found new things. These outlying objects here, number 1, number 2, in our Euclid terminology, they're a bit unusual if you compare with star clusters as we typically see them. Quite faint, absolute magnitudes of -5, and half-life radii of 15 to 30 parsecs or so. So they're sort of in this regime where you can debate, are these ultra-faint dwarf galaxies, or are they star cluster candidates? Okay, and you can look at colors, right? Color distributions are bimodal, as we tend to see in local galaxies as well, right? So this is maybe not super surprising, but it shows that, again, basically Euclid is suited for these kind of studies here. Yeah, maybe I'll skip over this very quickly. I just wanted to go back to the question of the expected versus the unexpected, right? So the ERO observations also had a program that looked at individual Milky Way globular clusters. So this was again led by David and Masadi. This is NDC 6397. You can zoom in, right, and appreciate the level of detail that you will probably see in a minute, right? So this is just zooming in on some small part, right? And of course, this almost HST-like resolution, but we get the whole cluster, right? Not just some pointed observations, which means that you can do very detailed studies at things like the surface density profile, probe down to very faint levels, 30 magnitudes per square arcsecond by counting individual stars. Right? And you can see that in NDC 6254, there's a little bit of an asymmetry here in the density contours that's actually consistent with what you then get from embodied models of the cluster as it orbits around the galaxy. Right? So you can also use these kind of things to look at the Milky Way potential. In NDC 6397, it's all very nice and symmetric, but we only see really the very central parts of the cluster. Right? It's much bigger than the Euclid field of view. It's very nearby globular cluster. So again, there will be many more globular clusters in the whole Euclid survey, right? So looking for streams and tidal structures around globular clusters, and other structures will be something very interesting to do. But then going a little bit to the unexpected here again, so you can do color magnitude diagrams, and one of the things that we thought would be nice maybe to do with Euclid would be to see if we could say something about multiple stellar populations, right? You see color spreads, or you expect to see color spreads due to variations in things like oxygen. Once you get down to the very cool stars, you get water signatures in these infrared colors, and that should introduce color spreads. That turned out to be not so easy. But when you zoom in on these color magnitude diagrams, you start to see other interesting features, like this little gap here. So maybe, again, you don't see it so clearly in just the color magnitude diagram here, but there's like a little gap here on the lower main sequence that corresponds to a stellar mass of about 0.35 solar masses. This is a simulated color magnitude diagram, so this is work by Massimo Gricius, who applied the same kind of photometry methods that this group in Italy has been applying to HST images over the last many years, right? And so they were quite quickly set up to do this with Euclid. Very exquisite photometry, and so you see again this gap here zooming in, and you see very clearly in the luminosity function, right? So here is the brighter and fainter stars, and there's this deficit of stars there. So what is this gap? Well, this is an effect that has been observed in Gaia. It's called a convective transition gap, right? So it's the mass where low mass stars go from being fully convective to not being fully convective anymore. And so that introduces that discontinuity in the mass luminosity relations of individual stars. And you can see that it's a very sharp feature, and so it's interesting potentially as also as a distance indicator, right? But you need large samples of stars to detect this, right? So that's the key why it hasn't been seen in HST studies, because typically you don't have enough stars to work with, and of course it has to be deep, right? So that you can get down to these very faint stars here. So that's the first detection in a globular cluster. 47 TOC actually shows the same thing, right? It's a bit more metal rich, so NDC 6397 is quite metal poor, but you see this feature also very clearly in the color magnitude diagram of 47 TOC. And of course, 47 TOC is located near the SMC, so we'll also have a nice color magnitude diagram of SMC stars in the background. But other people will be looking at that. So here's NDC 6397, where you see this gap. Here's 47 TOC, and then it has also been detected actually in Gaia observations of Milky Way stars, but first time in globular clusters. So I think that brings me to the end of the talk. So I've covered quite a few different things, but here's a little bit of a summary. So I started out talking about the ELT, and I think that for extragalactic stellar population studies, this is really going to be very exciting. this whole field of stellar archaeology is something that really take extragalactic now in a sense that we haven't been able to do before, right? With individual stars, but also pushing even further away with globular clusters, and of course there are many other things that we will talk about later this week that can be done. So the brightest AGB star, the brightest RGB stars, we will probably be able to observe spectroscopically out to about 3 megaparsecs with ELT. So beyond that, you still need to rely on globular clusters that we can observe much further away than that. Of course, for the younger people here in the audience, this is going to quit in a minute because I lost the connection. But there's just 3 bullets left, so I'm not going to spend time bringing this back up. I'll just make sure that I can see the slides here. Right. So one of the bullets that you're not seeing now is that observing time on the ELT will, of course, not be unlimited. Right? That's something we should keep in mind. It's 1 telescope, and so if you're used to thinking about the BLT, where it's hard to get time, but there are 4 telescopes there. Right? With the ELT, there will really just be 1. So you think more as a comparison with JWST or something like this. Right? So this is going to be very competitive. So we have to think about which targets we are going to prioritize. Right? We still have some time, but not too much time. Right? So this is something to get involved in if you're interested and want to make sure that your interests are going to be taken into account. Then the other thing was stay tuned for Euclid DR1, and then the final one was expect the unexpected. Right? I think that's a good way to conclude. So thank you very much for your attention.
Do we have questions? Thaisa?
So Euclid is only, it's more near infrared.
Yeah.
The V's you mentioned is from 6,000.
Yeah, it peaks at around 600 or something like this, right? But it's quite broad. So it's basically it's a RIZ. It's the RINZ bands, right?
Okay.
RINZ, yeah. So it's not so ideal for stellar population studies in that sense, right? Where you really would like to have the blue.
Yeah, you have to invent other.
Yeah,
colors.
So the thing, of course, about Euclid is that as a survey we have the satellite, but it's also going to be combined with ground-based supplementary observations. So Rubin is going to be part of that, right? So there's collaboration with Rubin that will give all the way into the UV, right? It will take some time before Rubin gets deep enough and has covered everything, right? But eventually Euclid will be supplemented with Rubin. And in the meantime, there are other surveys that are being included, right? So in the north, that's Union's survey, and in the south, it's DES, right? But that complementary ground-based photometry is important, and it's also for the cosmologists, right, to get photometric and so on.
Yeah, the Roman also will have clusters, but it's also infrared.
Roman, yeah. So Roman, I think, it's a bit more flexible, right? It's more of a general purpose observatory, of course, and it has a wider complement of filters. It still doesn't go very far in the blue, right? Yeah, as far as I'm aware. Yeah. And it's a smaller field, but it's a bigger telescope, right? And then you can sort of do more, and it will cover the galactic plane, which Euclid doesn't do at all, right? So I think those are very complementary things, right? So Roman is for sure going to be very exciting as well. Yeah.
And politically, it's hard to combine Rubin and Euclid because we have to wait for them to become public. Because you cannot work with them.
That's true. Yes. So this is a whole other level of complication, right? Of course, how to do this, and there's actually a working group that's working on shared data products, right? What can you share between the two collaborations, right? Ideally, it would be great to just say everybody's available for everyone, but it's a little bit more tricky than that, unfortunately. Yeah.
Rogério?
Thanks for the very nice talk. So I will try to put together your last part and your first part. Okay. So since you have multiple populations in the clusters, how does this affect, for instance, the determination of the alpha elements things on the integrated spectra of the GCs you are trying to do?
Yeah, that's a great question. Of course, the multiple populations affect the elements that are involved. there, right? So mainly the light elements, as you saw, magnesium. So if you really want to do galactic chemical evolution, you have to be a bit careful which elements you look at, right? So there are some that are probably quite safe. I think silicon, calcium, titanium, iron, most of those elements are not typically varying inside globular clusters, but you have to be careful about things like sodium and oxygen, magnesium, aluminium, right? So that's just have to be aware of that. But when you look at sodium, I don't think I show sodium, but you see that the sodium measurements that we get from the integrated light measurements are always higher than what we see in the field. But it's a little bit tricky because you don't know what the sodium abundances are of the beam stars and the galaxies that we're looking at. So that part is a little bit difficult.
Marina?
Thanks for the nice talk. It's a very simple question. What's the surface brightness limits for the L1 of Euclid?
The surface brightness limit. That's a good question. I don't know the number off the top of my head, and I think it depends a little bit on how you define surface brightness, right? Because if you look at individual stars, of course you can go down to I think 30 here, right? But if you're looking at diffuse light, it's a different story.
Yeah, diffuse light.
So there are definitely papers that have looked at that, but I don't have the number in my head right now. You can find it in the Hunt paper where we looked at that, but I'm not going to give you a number now because it's going to be wrong. But that has been looked at. Yeah, and it's quite good actually. So especially in the infrared, as you can imagine, and Euclid is it's optimized to eliminate stray light, scattered light, right? So it's a very good machine for looking at low surface brightness structures. Yeah. But we can talk later, and I will point you to the numbers. Yeah.
Do we have more questions from the students? If not, you have to meet the speaker. Okay, I have a question. Maybe now you cannot share.
I will try if you require me to share.
So the process of the Hunt paper of finding the GCs in NGC, I think 2403. First, you found the ones that were just like in the outskirts, and then you went and did the things in the inside of the galaxy. How was this process?
Okay. I'm not sure I need to skip through this. I mean, so
there
we are. Right, it's coming. I think
it's coming.
There's a little bit of delay. Right. So we started with the outer ones because those were the easy ones, and there was a little bit of pressure, of course, to get these papers out on a short time scale. Right. So we started with those outer ones, and then we sort of worked our way inwards. But it was basically, for a very large part, visual inspection. So we started with some simple magnitude and size cuts and things like that. Right. So there was no pipeline data here, right? So we just ran source extractor, and then we had some color cuts, and we measured sizes of the clusters, right? Eliminated most of the things that were unresolved, foreground stars and things that were very big. And then we were left still with a few thousand sources that we had to inspect visually, right? And so it was 3 of us who did this, and me and Ed Ferguson and Jess Howe. So we looked at all these sources, right? And ranked them, and this one is definitely a cluster, this one is definitely not, and this is maybe, right? And then we had a scoring scheme, and this is probably what you see actually in. It takes a little while. I think here, when this plot comes up, you will see that the sources are actually marked by.
There's too many transitions.
Too many transitions. In the color magnitude diagram, you will see that each cluster has a score, right? So a 1 is one that everybody agrees was a cluster, and then you go down to in a minute right here. So 1, those are the open circles there, and you don't see that very well. So they're open, but they're a little bit filled inside, right? So there are different kinds of circles, right? Some of them are filled, and some of them are completely white inside, right? So that is saying a bit about the confidence. But it was basically visual inspection going through all these lists. So that was the process, and that was easier to do in the outer part. also because there were not so many candidates. But when you go into the central parts of the galaxy, this gets really challenging because even if you apply color cuts and size cuts, you end up with all kinds of things that can sometimes be very hard to classify, and you have to look at large numbers of sources, right? Just in the crowded regions of the galaxies. So that's a bit annoying, right? But on the other hand, I think Euclid's strength is maybe more looking at these outer regions, right? Because the inner regions of galaxies, there are maybe better ways to do that, right? I mean, so maybe we should focus on the things that we can do well with Euclid. Yeah.
Cool. More questions?
I have one follow-up
Okay.
question related to your answer, because actually using your sentence that you should expect the unexpected. About these color cuts, just a philosophical question, because they are built in prior knowledge from a subpopulation. So by design, if you're expanding the population, you're probably expanding the phase that these objects occupy.
Yeah.
So you create this kind of circular problem.
Yeah.
How do you plan to deal with it? Because in the end, I guess, some updates need to be done, what needs to be a GC in some feature space. Is there any philosophical discussion about it?
It's always this trade-off that you have to make, right, between being false positives and false negatives in a sense, right? So this is a color distribution that comes out, right, and we try to be generous in these cuts, right? But especially on the blue side, it's really hard to tell from Euclid colors what is a globular cluster and what's a young cluster. So that's one of the things. I would not put my head on the block and say that some of these are not actually young star clusters, especially the ones in the inner regions. This we cannot tell from Euclid colors, right? So that actually makes a difference to the number of sources that you get. If you make a very blue cut here, you're going to get an enormous number of things that are definitely young, but there's sort of a place here where you have to make the cut and say what's the color, what's the bluest the globular cluster can be, right? So say a -3 metallicity or so, right? And as old as something very old, right? Okay, that gives you a color. And even if they are much more metal poor than that, the colors are not actually going to change that much once you, because the colors are quite red already, right? So the sensitivity is limited. Yeah, but of course there might be some weird object with a weird color that you're gonna miss, right? And so that's always, I don't know if there's that unique answer how to do this, right?
Yeah, because it led me thinking when like there aren't so many in your paper in the outskirts of 2403. Maybe there are some other ones there that are lower mass.
Yeah, that could be.
Are
I don't have the plot here with the luminosity function, so we
but
go
we can talk later.
in NEC 2403. I think we go about a magnitude and a half below the turnover. Right? So there are probably some even fainter ones that we haven't found. Yeah, it's not complete down to the very lowest masses. Yeah.
Cool. So let's thank Søren again. And now the students are invited to meet the speaker session that's going to be led by Victor and Niro in the room next door.
Okay. Should I
You can turn it off.
bring this?
Nós temos uma reuniãozinha nossa do LSST. Tu vai ficar ajudando a Ana aqui ou tu
Sim,
pode ir?
precisa ficar só 15 minutos.
Uns 15 minutos. Tá, depois tu vai lá no laboratório, Vitor, vai no